Hey guys, how's everything going? This is JSer, and in this video I'm going to take a look at 987 vertical order of traversal of a binary tree. We're given a binary tree, return the vertical order of traversal of its node values. For each node at position xy, its left and right children respectively will be at position x, y minus 1, y minus 1. Okay, so every node has had its coordinates. Running a vertical line from x to y from left to right. Whenever a vertical line touches some node, we report the values of nodes in order from top to bottom. Okay, if two nodes have the same position, then the value of the node that is reported first is the value that is smaller, and it will return the list. Like 3, 9, 20, 15, 7, 3 and 5, 15 are at the same x position, so 9, 3, 15, 27. For this, of course, it's 4, 2, 5, 4, 2, 1, 5. So 1, 5, 6 are at the same, right? Same x position. So 1, 5, 6. So actually, we have did a similar problem, which is 3, 1, 4. Binary tree vertical order traversal, which is basically the same. You see, for this case, we return 9, 3, 15, 27. And actually, the test case is the same. But the only difference is that is for the original position, original 314. If there is some two nodes at the same position, we return it from left to right. Yeah, if two nodes at the same row, the order should be from left to right. Right. So at that program, we use a BFS, which loops through all the nodes layer by layer and from left to right, and dynamically change the index. But now we need to put the smallest ahead, right? Okay, so for detailed explanation, please search on my channel for 314, and here I'll just do a brief recap. So for the case of 3, 9, 20, 15, 7, if we just take a look at the root node, it must be 3, like something like a 3, right? And now, if we take consideration of 9, 20, if we just look like 20, and we can just push 20 in, right? Because it's on the right. But now there's a problem. 9 is from left, so if we take 0, think the root node has an x of 0, then there must be minus 1, right? But for array, there is no minus 1, which is if we insert an element here, actually the whole layer must the odd nodes of the same layer must have a bigger index, right? If we insert 1, then originally this minus 1, this is 1. But now the index must be 0, 2, right? And the 3 will be just a bit pushed there, so it will not be touched, so it's cool. So this is our idea. We just loop through all the nodes layer by layer, and for each layer, if there is a negative index, okay, let's see. We use a queue, which is an array of node index, and for node we get the index from the parent node, and if it is minus, insert an array at the result if index is smaller than 0, and shift all the indexes of that layer. There's just one problem. Before we just push our node for the conflicting nodes problem. If two nodes are at the same index, which originally in 1314 we just push them, right? Push them from left to right, just as the order we handled the node. But now we need to sort them, right? So before we push to the real result array, we need to actually cache the result and do the sorting and then push the final result. Okay, let's try to do it. I'll just copy and paste our code here, and I'll do some brief introduction, and I hope you can understand. This might not be the best solution, but I think it's pretty easy to understand. Okay, so we have a result array. Okay, this is a root. We pushed the root node at the queue, in the queue, and with a start index of 0. And then every time we will get all the elements out, which is here. We push null as an identifier. We get the head out and check if its index is negative. If it is, we say set the flag, left node inserted to true. So, and then we unshift the empty array, and for all the indexes, if a new element is shifted, so all the index must be plussed with 1, right? So this is a real index of this node in the result, and then if the index the array is not yet, we create an array and insert at that index, and then we push our node value in, and then we push left and push right. So we need a little change. Rather, here we just push the result directly into array, but actually we need to cache it. There might be multiple nodes in this position, and we need to do the sort. Yeah, so we will create for each layer is here. We create to map, like a diff map. Okay, a new map. So we will update to the index current. So the result index is we can update the result, and also we need to update the map. So diff map has current index, doesn't have index. We set it to an empty array. Right? Yeah, and then we could diff map get current index and push, right? We push the node value in this map, and for each layer, when everything is done, we need to do a little sorting, right? So for let index AR of this diff map, first we sort, and then we push to the right result, right? Which means the index we will push ARR. So we do a little tweak. We tweak a little of the original solution by adding a cache map and sort the array before we push to the final result. So this might work. This, of course, not. Push is not the direction. Oh God. Cool. Accept it. Let's try to submit. Woo! We got a wrong answer. Actually, I got the wrong answer at the beginning. I just want to show why our original solution doesn't work. You see, actually, we got something like this. So the output is like this, and we expect it like this. So after I dig for like an hour or so, I found that I had a very serious bug, which is also in the 314. So the original solution doesn't work actually, but the test case of this LeetCode problem doesn't cover my error case. So I already submit a contribute. I contribute to the LeetCode and hope they could update the test case. So there's a problem. You see, I only set the left node inserted true when the index is minus, right? But actually, if you take a look at the array, like some complicated tree, for example, the input like this, LeetCode has this nice feature of tree visualizer. You see, might be a case that the leftmost node will not just be at the top position, a higher position. Like for suppose this is currently this 26 is the leftmost node, right? But there might be some nodes from a right tree and blah blah go, and then it will go to the 26th layer, right? But even it will go straight left, right? And so the leftmost node might come from the rightmost node from the parent layer, right? So our assumption here is actually invalid. Like here, if it is smaller than 1, is negative, we set the flag to true. But actually, the position doesn't matter. Any one, what we want to know is that in this layer, is there a negative value rather than the first negative value, right? Even if we find a negative index at the index of 3, we still need to update the index of the node at the beginning, right? So I think you now understand what I understand the problem. We should not update the flag and the shift and set the current index here. Rather, what we do, I'll keep the node, keep the flag here, and but I will not shift it now. I will wait the whole layer to be traversed, and the index I will not update it now. So I will not. Still, I will not update the result right now. And still, for diff map, I only care about the real index, the original index. You set it, and then get it, and then if we push a new node, there's a problem. We push the node. If we push it, okay, we can just push it. So now we get from the diff map the index, right? We sort it. Yes. And but the real index is, if this flag is true, we should say that real index plus 1. If not, it's self. And then if result real index is undefined, result is should be empty, right? Cool. And then we could say we push all the elements in. One thing, update the nodes, the child nodes, which are already in the queue. We have the if clause here. If this, we will for net element of Q, element 1 plus 1. So this should work, right? No? Oh. Even for the simple case, we still does not work. Still not work. Let's see what happened. So we get a node from index. If it's more than 1, we set the flag to true. Okay. The diff map of index, we set to the index. Cool. And then get index, push node value. If node left, we push. Okay. Until here, I think it's right. And then we get the element from the diff map. We sort the array. The real index should be plus, so, and then we push the result. And if it is inserted, we for each element in the queue, we update the index. So I think this should work, man. Allow me to log the console log. I'll log what? Q. First we get 1, and then we got 2, 3, and then 4, 5, 6, 7. The index would be the original one, 0. Cool. And then next one would be -1. Okay, -1, 1. And then actually we update it, so 0, 1, 2. So there should be -1, 0, -1, 0, 1, right? 0, 1, 1, 3. And then the real index is this. Okay, console log diff map. So the first one, the map would be updated to set the 0 to 1. Okay. I'm sorry, I need to log the result also. So, okay, the original empty, we need to set the 0 element to this. Right. Cool. And now we get the second one with 2, 3, -1. This is right. And then the original become this, so we need to insert -1 with 3 and 1 with 3. -1 with 2, 1 with 3. So now here becomes a problem. We get the index, which is -1, and the is node, left node inserted. We said it's true, right? So if it is true, its weirdness must be 0 and 2. I know what happened. God. We should first, here, my bad. We should shift to the unshift at the beginning. So this will work. Yeah. I know what is bad. Seems good. Cool. Wow, we're really fast. Wow, that fast? So it's not stable. So it's pretty good. Let's try to analyze the time and space complexity. Of course, for this while loop, every node is traversed, okay? And then every node is traversed, nothing special. We're using a map, okay. It might cost an extra space, but the time would be constant. We shift, okay. For now, we sort. So this sort is actually a problem. For this sort is actually a problem because sort, you know, is n log n complexity, and this is linear, and then we are linear of this. So actually, we need to do some how to say that to suppose the tree would be some like evenly distributed. So there's n node, full tree. Let's say it's full tree, which means for each layer, there will be I will be 2 to the power of I elements, right? If this is the case, this is the best case, I think. Best case? I don't know. Just so for the average case, if that's the case, there will be a maximum for each node. For each layer, their maximum, just like we're doing analysis here. Analysis here. How many nodes will collide? Here, go here, then go here. There will be 2 nodes here, right? 3. If you draw a map, you will see that there's a 3 node here, and then this. Wait a minute. This will be 2, 1, 1, 2 will be here, so this will be 3. So here will be 3, right? 3, 3, 1, it will become 4. Wow, this is hard. This is hard for each node, for each position. There will be 2 node. What's the time complexity? Wow, this is hard. Okay, let's say I asked him to understand. So for each layer, there will be actually 2 to the power of I elements, right? And there will how many positions? There will actually be like at index 0 there will be 1. So actually I plus 1 positions, right? So averagely for each position at layer I, there will be 2 to the power of I divided by I plus 1. These kind of nodes, right? Averagely. So this will be the this will be used for the the time complexity of this sort. Right? So averagely, this will be take like this. Let's take this number as sets it to like AVG. Okay, yeah, I just say the AVG, and so the sort will cost log AVG and log AVG, right? Just for the sort, and they will be they will be I plus 1 node. Is it? Yeah. So this will be the whole time complexity for one layer, right? If it is like a full tree, and we will just sum this up, right? And then if we can take this averagely, a little more averagely, it would be like for n node, for layer, for n nodes, like a j layer height, which is height with j. Averagely, it will be n divided by j layers, right? So it's actually will be like times for each layer. It will cost us with this. Oh, yeah, this. Averagely this. And remember, there's still we need one extra I plus 1 to set update the index, right? But it's obviously smaller than this, so we can omit it. I'll just put it here, I plus 1. Okay, so what this would be? Average log averagely. So this will be I plus 1. We divide times this, so it will be gone. I n divided by j times 2 to the power of I. Okay. So I equals okay. No. I made a mistake. So if we don't care about the I problem, we say like for n node with the height of j, so averagely will be n divided by j elements, nodes at each layer, right? At nodes at each layer. So the problem becomes, well, how many layers? Well, j, right? Times with 2 to the power of this is the this is the amount of nodes. So this is the nodes, right? And this was divided by I. What is I? Nodes. How many positions? Averagely? Wow, averagely will be 2 J. Oh, wait a minute. This is the amount. This is the amount of. Wow, what's the time complexity? It's hard. It's really hard. Let's suppose that these are not a tree, like for like a square. So this will be n nodes with j layer, and for each layer there will be n times j nodes, right? But for position, for this one 0, last would be j. Last one would be j divide. Last one be the 2 to the power of j. Right? Two to the power of j. Oh, this is hard, man. And what's the time complexity? Wait a minute. 1, 2, 4, 8. 1, 4, 8, 16. This is 2 to the power of n. This is 8 minus 1. This is actually 16 minus 1. So 2. One plus 2 plus 2. Okay. So, wait a minute. So let's suppose it's j layer full tree. So the node count would be 2 to the power of 0 plus 2 to the power of 1 plus plus 2 j minus 1, right? So actually this equals to 2 to the power of j plus minus 1. So actually this is something like this. Suppose the count is n, so the layer would be log 2 n, right? The layer would be this kind of layer, and for this assumption is right. For each layer, for each layer, I averagely it would be 2 to the power of I plus divided by I plus 1, right? For each layer, average this to at each position. So the total sum would be like we traverse through for the first layer, it would be, of course, it's gonna be 1, and the second one will be the count is 2, right? 2. 2 times, this is 2 times 2 to the power of I divided by I plus 1, not 2, 2, divided by 2, wait a minute, this is the count of the sum. Oh god, this is hard. It should be sum. So averagely this will be this node, so this node. Okay, then this one times log itself, right? And then we times the position, right? For each position, averagely, for each position it will be this count. So the sort will cost us this time for each bucket, for each position, and then we time the position, which is like this. So this will be the for each layer time complexity, and sums will be I from 0 to log n, right? Well, we need to break this up, so this will be gone. So the problem become for 0, so 1 times log 1 divided by 1 plus I equals 1, 2 times log 2 2 divided by 2, so it's still 2 divided by 2 plus 3 log 4 divided by 3. It's not 3, man. It's 4 plus 5 times log. This should be not 5, man. It should be 8, but not 8 by 4. Blah 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 blah, right? Log actually could be changed to subtraction. So log 1 divided by log 1 plus 2 log 2 divided by log 2 plus 4 log 4 minus log 3 plus 8 log 8 minus log 4, blah blah blah. So finally it will be the total will be n. So this one will be n divided by 2 times log n divided by 2. So suppose the account is 2n, okay? Suppose it's 2n. Suppose it's 2n. Let's say, so it will become n log n divided by the j layer, right? J layer. Okay, so okay, so forget about the n. It's 2 to the power of j, 2 to the power of j divided by j log j plus 1. So this is our result. Could we do some averagely? Something average? Wow. I think I'll give up on here. Actually, I don't know. I cannot derive something better than this. Suppose. What about another rough explanation? Suppose there are n nodes, but m position. Well, position which depends on the height and nodes, right? If we can do this, I can actually think that for each node, there will be for each position m, there will be n divided by m, this kind of nodes, right? So times log m divided by m. This is a time for each position, and finally we get m. So this will averagely m times log n divided by m, right? This kind of time complexity, n nodes, m position. For each position, there actually will be this kind of a node, so we sort them. This is the sort, right? N log n. Cool. And then there will be n position. And we sort it, and we also will plus the node. Traverse the node, right? This is actually plus n. Well, so actually we could, it's almost something like this. Okay, and plus mn. This looks better. Maybe it's right, maybe it's not. And about space, this is time. This is the best I can do, man. For the space, okay, we use the Q, or maximum will be this one, right? This the layer count. So basically it should be half of the I think half of the node. Okay, so it's linear time up to the n. This is linear to the n. And other, again, we use a map, which is actually the position for each layer, but it was smaller than n, so it's linear. And yeah, I think this should be extra would be linear time. And the result will not be counted as extra auxiliary space, right? So yeah, cool. So I think that's all for this problem. Hope it helps. And yeah, see you next time. Bye bye. I hope I'm not wrong. Let's take a look at the solution to see if it's good or not. So it says what n? So what here? Let n be the number of nodes. The time complexity would be L log k, width of the tree. What is width of the tree? K is also the number of columns in the result. What we got is log for each position. If the position, I don't know, width of the tree. width of the tree. So each list. That's also cool. So it means rather than we count all the position, it will say it's much better than we compare the whole list, right? So for the whole list, it will be this kind of amount. Listness, yeah. So actually, suppose k x positions, averagely, it will be n divided by k for each list in result. So because we're sorting sorting for each layer, so it's think of divide and conquer. It must be better than sorting the whole list. So it will be better. Say it will be better than n divided by k times log n divided by k and times k, right? So it says it's the upper boundary would be n log n divided by k. So actually, it's kind of similar to us, right? Because actually, we're thinking that we rather than we divide it by each list, it's this big list. We actually think of them each at position. So yeah, I think that's cool. I think we are thinking the same way. Yeah, that's all for this one. Hope it helps. See you next time. Bye bye.